All right, hello everyone. Welcome to my channel. I am Thomas, and on this channel we do educational videos on various different subjects, mostly the esoteric and obscure. And today is, I don't know, the 121st or second video here on the reciprocal system of theory. And the reciprocal system of theory was originally devised by Dewey B. Larson back in the 20th century. And it is a theory of everything. It is a system of theory, meaning that if you understand the system, then you can apply it to any subject that you like. You have to be somewhat fluent in the system, understand how it works, understand how you approach it, and then you can apply it to anything. Larson did just that. He applied it to chemistry, to physics, to astronomy, to economics, and eventually even to metaphysics, to religion, philosophy, and psychology, and did a pretty good job with all of it. Made a few mistakes, but he admitted that. He admitted that he was prone to make some mistakes. He said that the system itself is correct. Whether I have applied the system correctly in every instance is another matter. But if I didn't apply it correctly, those mistakes will become apparent over time. And so he did make a few mistakes, and some of his followers and revisers kind of caught those mistakes and have moved the theory forward, especially KVK Nehru and Bruce Perret have really moved the theory forward. And now it's in 2023, it's waiting for, a group of people such as yourselves and me to take the mantle and, push it forward a little bit more, because it really could shed light. And it really is a leveling force, because if we learn the reciprocal system and learn to use it, we don't have to rely on these people with the white lab coats on. We don't have to rely on the dudes with the frocks to tell us what we're supposed to think about this and to give us the science. We are able to figure out the science for ourselves. Okay, so now what we're doing here is we're going over one of the interviews that Larson did in 1984. He was already 85, 86 years old at this point. He would die about 6 years later. And he's interviewing with this guy, Jan Sommer, and they are just kind of going over how the theory evolved and, where it came from. And he just got done kind of talking about how there were two phases of the research. First was the inductive phase, which he called really uphill, and then there was the deductive phase. And in the inductive phase, all he had to go by was kind of like the measurements, taking like the periodic table, the elements of the periodic table, and looking at their various stats, their density and their atomic number and their, permeability, or, whatever kind of metric that he was focused on, and going from those basic principles to individual, from specific to general. So going from those individual numbers to a general kind of rule. And that's where he eventually arrived at the top of that, at his fundamental postulates. And then the downhill phase is then to take those fundamental postulates and apply them. If this, then that. If this, then that. And the postulates were the if. Okay, if the postulates are true, then this is true, then this is true, then this is true. So going from the general to the specific. Okay, now we're going to take over here. He had just gotten done He said, I threw out 2 years of work and started back on a different basis because he's been messing around with the elements of the periodic table and kind of figuring. He's thinking that the periodic table has these two different bases, um, parameters, rows and columns, and they each are measuring something. But he's recognizing that there's kind of something missing. That there's really actually three numbers, and the periodic table is only taking into account two numbers. Okay, so here we go. Question: how long did the deductive phase last? Larson, I would say it must have been about 5 years before the publication of the structure of the physical universe that I finally started downhill. Question: until that time, you were concerned with formulating the general principles? Yes. Answer: yes. Up to that time, I had been working from the basic information, the basic observations and measurements, and trying to get the general principles controlling them. Particularly at that time, I was very much interested in finding the reason for these equations I had developed for the interatomic distance. You've seen the equations in the book. They're simple enough. But what do they mean? That's the old problem of present-day physics. They have so many of these nice equations, but they don't know what the various quantities are that enter into the equation. They don't know what they signify. In fact, there are some scientists dealing with those things that contend that they don't have any meaning, that the mathematical expression is the whole thing. But I was trying to look for the meaning. Question: do you remember anything about the circumstances of your discovery? Larson: I had this mathematical expression on the interatomic distance, and I remember this particularly. I was on a trip driving down to Corvallis, Oregon, and about halfway down there it struck me that this expression that I had found for the interatomic distance was the integral of a reciprocal relation. So I said to myself, well, what does that mean? Well, then I realized that we actually have a reciprocal relationship here. What we're doing, we're getting the summation of it over an area or a distance. And then I thought, well, now, if that's true, if there is a reciprocal relationship here, what if it's a general relation that applies all the way through? So I started thinking, what would happen if there were such a general relation? And I could see right away that that answers a lot of questions. By the time I got down to Corvallis, I could see that this would open the door to the solution of at least a half a dozen problems of long standing in the physical sciences. It was like rolling up a curtain, and you've got a bunch of answers right in front of you. Okay, now we're going to go into what those answers, what those questions of long standing were in just a second. I was remiss. I didn't really give you kind of a summary of really what the reciprocal system is about, where he's talking about this reciprocal relationship. The basic idea with Larson's postulates, which he's getting to the point of formulating right here, is that we live in a universe of motion, not a universe of matter and not a universe of energy, but a universe of motion. And motion, matter and energy are in fact just specific kinds of motion, along with all other of these different scientific quantities, such as pressure and acceleration and force and gravity and energy and electric charge and electric current and magnetic flux and permeability, permittivity, and uh, density, any kind of different scientific quantity is is just a kind of motion. Now, other people had come up with these various universe of motions, including Thomas Hobbes and Arthur Eddington, Rene Descartes. But Larson distinguished himself from them by defining motion as motion is the relationship between space and time. In fact, at the beginning, Larson was actually just calling motion space-time. Then he began to call it motion and as the relationship between space and time. He also called it change in 3 dimensions. And the 3 dimensions that he talks about a lot here comes from the qualities that he observed in space. Space has 3 or more dimensions. And when you have this relationship between space and time, what that's implying is a reciprocal relationship. Just in the same way that 3 halves is the reciprocal of 2/3. Time and space don't exist separately from one another. They exist in a fraction, with time being either the numerator or the denominator and space being the other one. But time and space, so time and space basically have the same qualities, but they are reciprocals, but they are inverted. And what we know about space is that it is coordinate. It has 3 or more dimensions. And Larson calls that coordinate, and others call that coordinate space. But Larson made the leap to say that there is also a coordinate time. Because there's a coordinate space and they are reciprocals of each other, and so therefore what adheres to one quality adheres to the other. So we've got coordinate space and coordinate time, 3 or more dimensions of each. What we know about time is that time is progressing. It's always getting later and later and later. It's flowing. So therefore space also has that quality. Space is progressing or flowing. Things are always getting farther and farther apart. And that was observed by the Hubble telescope way back in the 1920s as the recession of the distant galaxies. Larson calls that clock time and clock space. So he starts with that general reciprocal relationship, and he was able to construct an entire theoretical universe from that starting point. That's really the essence of his first of 2 postulates, and the second one is really mainly just about geometry and mathematics. The other aspect of the first postulate is that space and time only come in discrete units. They're not continuous, they come in chunks, they're quantized. And so when you talk about all these different scientific quantities that I was talking about, pressure and electric charge and magnetic flux and acceleration and force, they're all relationships between space and time. So you can really plug them in to your classic equations of classical mechanics and see how they work out. Simple example would be just, this isn't classical mechanics, but relativistic, E equals mc squared. Energy, in Larson's system, energy is time over space. Matter, in Larson's system, is time to the 3rd power over space to the 3rd power. And then speed, as we know, speed is simply space over time. The car is moving 10 miles per hour, 10 miles of space in 1 hour of time, space over time at speed. So E equals mc squared, energy, time over space, equals matter, time to the 3rd power over space to the 3rd power, times the speed of light squared, s over t, the quantity to the 2nd power. You multiply all that out and you get time over space equals time over space. So the equation checks out. So you can use that system that Larson has devised if you know all of the various um, time-space components of the various scientific quantities. You can use that as a check, and a check for not only for the reciprocal system, but also for all these different equations. In the vast majority of the cases, the equations check out, but have been a few different situations where the equations did not check out. One example of that is electrical capacitance. And this one's kind of stumped Larson, and it really kind of derailed a lot of his theory into the electrical field. And Larson ended up having one different value for capacitance, and Bruce Perret and others eventually, decided that capacitance was actually S to the third power over T. As opposed to, I think Larson had it as a T over S relationship, which is not only energy, but it's also, in general, charge. Okay, now let's get back to Larson. I'm going to read the last two sentences of where he left off, and then we will get into some of the meat here. By the time I got down to Corvallis, I could see that this would open the door, this general reciprocal relationship would open the door to the solution of at least half a dozen problems of long standing in the physical sciences. It was like rolling up a curtain and you've got a bunch of answers right in front of you. Question: do you remember what some of those half a dozen solutions were? Larson: in the first place, it gives you an answer to the speed of light. It has always been a question as to why we should have a certain speed of light and not something else. What this quantity c, the speed of light, means. Well, if it's a reciprocal relation, the light has to go at unit speed. That's obvious, don't you think? Now, so I didn't explain that as well. So space and time are quantized. They only come in chunks. And in Larson's system, in Einstein's system, the speed of light is the maximum speed of the universe. Nothing can go faster than the speed of light. In Larson's universe of motion, it would make sense that motion is the background or the origin even of the universe, and that the speed of light is simply 1 unit of space in 1 unit of time, and that it is the midpoint of the universe. There's an entire half of the universe that's moving faster than the speed of light, along with the half of the universe that's moving slower than the speed of light that we're more familiar with. The slower than the speed of light section, Larson calls that the material sector, or sector 1. And then the half that's moving faster than the speed of light, Larson calls that the cosmic sector, or sector 2. And sector 2 and sector 1 are basically reciprocals of each other, meaning that they are exactly the same as each other, except that the roles of time and space are inverted. So whatever is going on in sector 1 is exactly the same as what's going on in sector 2, except that the roles of time and space are inverted. Okay, so he's going to go into that. Now, it doesn't seem totally obvious to me, where he says this, but something else, what this quantity c, the speed of light, means. Well, if it's a reciprocal relation, the light has to go at unit speed. That's obvious, don't you think? So that's what he calls the speed of light is unit speed. And then sector 1 is slower than unit speed. Sector 2 is faster than unit speed. But really, when you use the reciprocal relation, it's really that sector 1 is slower than unit speed in space, and sector 2 is slower than unit speed in time. And once you have that, that leads to the idea of the space-time progression, which in turn, losing my spot here, which in turn leads directly to the explanation of the recession of the galaxies and to gravitation. The nature of gravitation is that it's simply a scalar motion in opposition to the progression. That's kind of that kind of thing comes out right away. You don't get all the details, but you do see the general picture. And sorry to interrupt again, but Larson just actually is really just using the term gravitation there. That doesn't It doesn't have to be that term. For some of the people that maybe question the nature of space and the universe and astronomy in general, who question gravitation in general, this also could be simply something finding its level, like a density hierarchy. The denser you are, the further down toward the bottom you go. Okay, now back to the question. Could you put an approximate date on that trip to Corvallis? Larson, that was around 1950. Question, so that was the culmination of the inductive phase. Larson, that was the point at which we could say I could start putting the postulates together. It didn't take me long because all I had to do was to postulate what I needed at the time and set up these ideas in a more complete fashion, with the understanding as I started working on it that if I needed something else, I would put it in later. As it happened, I actually took out some rather than putting more in. But all this was done in a relatively short period of time, so essentially the postulates followed almost immediately after getting the idea of a reciprocal relation. The only reason that it struck me and that I still remember where it was is that when the thing dawns on you, it's kind of a landmark, so to speak. Okay, we'll stop there for today, and we are getting fairly close to the end here of this interview. We will take over tomorrow. Thanks for tuning in. Have a great day.